All right, so now what we've just been talking about falls under the classification of thermodynamics. And this is, what would happen at equilibrium. These are these sort of energy values that you would measure if you allowed your reaction to go to equilibrium. This is something that's commonly confused with kinetics, which is how fast a reaction occurs. These are actually two separate things. They're similarly related, but they're separate. So we're going to pick these apart and see if we can't understand a reaction from a thermodynamic perspective as well as a kinetic perspective, and then kind of bring the two together. Okay, so first of all, what do we mean by equilibrium, like a kinetic equilibrium, or I'm sorry, a chemical equilibrium here. So let's just take this reaction here where we start off with A plus B and they're going to react to form C plus D. So in terms of my free energy diagram, what is that going to look like? So sort of how I think about this, and this is a common way to think about this, is at first you're starting out with everything on your reactant side. You only have A and B, right? So that means that everything is over here. So I think of each of these little dots as a reaction that could occur. So first, everything's over on this A and B side. Once you say go, once you mix them together, they're going to start reacting. Well, so what does that look like? That means that each of these little balls is going to have a chance to climb this hill and fall down onto this side, right? So I'm going to start losing things from one side, and they're going to appear on the other as this reaction occurs. Boom, boom. Remember, this reaction is occurring because I have these collisions that are occurring between A and B. So A molecules combine with B molecules in such the right way, and then they get converted into C and D. So after some time, I have, something like this here, where now a majority of my reaction has occurred, and so I have more of C and D. Well, C and D can combine together, or can start, once those concentrations build up, they're also going to start colliding together. And there's the chance that they're going to move back over to this side, right? So every once in a while, I'm going to lose one of my products over to the reactants. And I'm going to lose more reactants to products, maybe every 2 goes over here for every 1 that jumps back. Eventually, I'm going to establish an equilibrium where the concentration of A and B don't change, and the concentration of C and D don't change. This could be a dynamic equilibrium where in fact they are switching sides. They're just doing so in such a way that for every time I lose some A and B, I'm also losing some C and D. So they've come to this equilibrium where the overall concentrations of A and B aren't going to change. So that's what an equilibrium is. Once you've waited long enough to the point where you've reached this sort of steady state concentration, okay? Yes. So then each reaction also has this characteristic equilibrium constant. So this is the value of the different, the ratio of concentration of products to reactants that you will get at equilibrium. So, you want to just think products over reactants. That's what I have nailed in my mind. In this particular reaction, again, where we have A plus B going to C plus D, my products would be concentration, right? That's what these brackets mean. Concentration of C times the concentration of D over concentration of A times B, right? So that's my products over reactants. So when KEQ is greater than 1, looking at this equation here, is that going to favor products or reactants? So KEQ greater than 1, that means that this term on top, my numerator has to be larger. So this is favors products. Likewise, KEQ of less than 1 favors reactants. And what about when KEQ equals 1? Then I have equal concentrations of products and reactants, okay? So this is product concentration equals reactant concentration if KEQ is 1. Okay, turns out that your equilibrium constant is exactly related to the free energy change in this reaction. okay? So then let's just sort of make a little diagram here, and it's related in terms of R, which is the ideal gas constant, times temperature, times the natural log of the KEQ. So it's a log relationship. So that means if I'm going to have free energy and reaction coordinates, if I have, again, a KEQ of 1, meaning that my reactants and my products are equally favored, you can plug that into this equation here and see that that means that my delta G has to be 0. So that would be this type of reaction here. This is delta G equals 0, KEQ equals 1. So this is the type of reaction coordinate diagram that I would expect for a reaction where reactants and products are equally favored at equilibrium. They are sitting at the exact same free energy value. KEQ greater than 1 will correspond to a negative delta G. So that's then going to have a reaction on free energy diagram that looks like this, right? So now I have this negative delta G associated with this gap here. Okay, so you can see just how big that gap is will influence the actual distribution of products or reactants, right? If I have a KEQ that's way bigger than 1, it's going to be very favorable towards the products. That's going to be, you know, all the way down here or something like that. So the difference in our free energy diagram will correspond to the actual distribution of products to reactants that you get at equilibrium. Likewise, just to sort of complete this here, when we have a KEQ greater than 1, that's a positive delta G. So what would that look like? That would look like something like this, right? So now I have my positive delta G. Again, that corresponds to a non-spontaneous reaction or a reaction that favors the reactants. Okay? Okay, so now that all has to do with equilibrium. So the best way to think about the difference between equilibrium and kinetics is equilibrium is what's true when you let your reaction sit for 100 million years and then come back and see what happened. It's after everything gets established into that steady state. Okay, some reactions go to equilibrium very quickly, some take quite a long time. But that's what equilibrium, that's what those thermodynamic quantities are. They are true only when the reaction has reached equilibrium. So now let's talk about kinetics. Kinetics is the actual rate at which a reaction occurs. It's dependent on a few things. You know, first of all, reactions occur first and foremost because molecules are colliding together. So increasing the concentration will just have the effect of increasing the number of collisions that take place. Activation energy is something that we're going to see here in a second. So let's pause on that, but that's going to be a big influence in terms of how we draw our free energy diagrams. Temperature. Temperature will also increase. So this is number of collisions. Temperature will increase the number and energy of those collisions. Right? So when you increase temperature, not only do you increase how fast everything's moving around, so on average they'll collide more, but also those collisions have more energy. Another sort of more complicated factor would be geometry or sterics. So if your binding site or reaction site of your molecule is buried in a lot of steric hindrance, that'll just make it a slower reaction than if it's nice and exposed. And then a catalyst is a species that speeds up a reaction. And we'll see exactly how that's done here in a second. Okay, yeah. So these are just these factors that will influence the kinetics of a reaction. Let's focus on this activation energy here, because this corresponds to our free energy diagrams. The remember what we were talking about, a reaction occurring. We're going to start off with everything kind of on this side. And then slowly things are going to deplete from this side and end up on this side, right? as my reaction occurs. So to do so, these beads have to jump over this hill here. That hill represents the activation energy. That's how much energy those reactants need to have in order to actually make it to the product side. This is, where does that energy come from? Largely from temperature, right? So increasing temperature will increase this ability for these guys to jump over this hump, all right? This is the activation energy. So then we can sort of depict the rate of a reaction or reaction kinetics based on the height of that barrier, right? So if we look over here, you know, assuming I start out with the same sort of deal, this has a much higher activation energy, which means that the probability that one of these guys is actually going to gain enough energy to jump over that hump is that much less, right? Now notice that the delta G is the same for both of these. So if I left it for 1,000,000 years, they would eventually come to the same steady state concentration, the same equilibrium value. But the reaction on the right is much slower because it has a higher activation energy. So this is how we can represent the speed of a reaction or the kinetics of a reaction on these free energy diagrams, is the height of that activation energy barrier. And so this just kind of hammers this home, right? This idea that we have two different things at play when we're drawing these diagrams. One is the kinetics of the reaction. That has to do with the height of your activation energy barrier. That's representing how fast a reaction goes. And the other has to do with what happens at equilibrium, the distribution of products to reactants at equilibrium. And that has everything to do with this gap here, or that delta G. Right, so both of these pieces of information are contained on these free energy diagrams. All right, so let's take a look at comparing a few free energy diagrams here. So we have two different reactions, right? So what this is kind of representing is, let's say that we have A plus B, and they could either form C and D, or they could go in this other direction and form E and F, okay? What this free energy diagram depicts is that one of those reactions is going to be more favorable. So which one is that? So that would be this reaction here, going from A to B to C plus D. So why is that more favorable according to this diagram here? Well, first of all, the height of this barrier. My blue activation energy is much smaller than my red activation energy, meaning that that blue reaction will just happen faster, right? So if this is sort of a competition between which way does this go, it's going to go, in terms of speed, go to C and D. So not only that, but also we look at the difference in free energy between these, there's a much larger delta G. They're both negative, so they're both going to be spontaneous in that towards the products, but the CD reaction is a much larger delta G. So this is a reaction that's both kinetically more favorable and thermodynamically more favorable, the reaction from A to B towards C to D, right? And again, both of those being depicted on our little diagram here. Interestingly, something that occurs kind of often as well is something like this. So again, we have our same, I can color code things. That blue curve representing going to C and D. That red curve represents a different path where we go to E and F, okay? Now we have two different kind of factors at play here. If we look at the height of these activation energy barriers, the red reaction, you know, the reaction going towards E and F, is much faster than the blue reaction. It has a smaller activation energy. So in that sense, in the kinetic sense, E and F are more favorable. So these have kinetic favorability, whatever. But when we look at the thermodynamics, the delta G, the delta G of the blue reaction is much greater than the delta G of the red reaction. So my blue reaction is thermodynamically favorable. So there's this interesting push-pull, right? One reaction's slower, but my products are more thermodynamically favorable. The other one's quicker, but my products are less thermodynamically favorable, okay? So what's gonna happen? Well, it actually depends on temperature. You can use temperature to control between these two, right? So remember, temperature is going to be your ability to get over this hump. The more thermal energy you put in, the more energy it has to jump over that barrier. So that means that my thermodynamic product is going to be favored at high temperatures, when it has no problem jumping over those barriers, right? Not only would it not have a problem, you know, well, not have a problem, but it would be able to make it over the bigger hump. It also means that when something landed on this side over here for the kinetic product, it would be easier for it to go back too, to jump over that back reaction. However, if I didn't add a lot of thermal energy, I put in just a little bit of temperature, low temperatures, it would have a really hard time getting up that hill. And so this smaller hill is going to be the one that's more manageable. So kinetic product will be favored at low temperatures. All right, so that's a push-pull that we're going to see a few times throughout the semester here. You can tune a reaction to go one direction as opposed to the other by using temperature. Okay? Importantly, make sure that you understand how these free energy diagrams are going to be a big part of this chapter. So make sure you understand what they're really saying. That's the key part. All right, so we had all these other reactions that we were looking at were just one step. There was your reactants, then there was a single hump, and then there's your products. That represents what's called a one-step reaction. Many chemical reactions have many what are called intermediates. They occur in several steps. So this is an example of a multi-step reaction. In particular, there are 1, 2, and then finally my product 3. So this is a 3-step reaction. Okay. Obviously over here, these were my reactants. Over here, these are the products. These local minima in the middle, we call these intermediates. Okay. In theory, these are things that could be isolated, right? A species that could be isolated and studied, or at least measured or observed. On the other hand, at the peaks here, you have what are called transition states. Transition states are fleeting, meaning they only exist for a split second, right? If my marble is sitting at the top, it's either going to fall one direction or the other. It's not just going to chill there. They're the highest energy points on your diagram. All right, so first of all, being able to know that intermediates are local minima, transition states sit at the top, that's really important. Again, counting the number of steps given a free energy diagram, that's really important. Just to give sort of specific examples here of what a transition state would look like and what an intermediate would look like, let's take a look at 2 similar examples here. So this is going to be conversion from methyl bromide to methyl chloride or chloromethane, bromomethane to chloromethane. And this is going to be a one-step reaction, right? It's just reactants, hump, products. And this is my transition state, the highest energy state throughout this reaction. So in this particular case, what does that look like? Well, this is this state where my bromine-chlorine bond is half broken and my where my bromine-carbon bond is half broken and my chlorine-carbon bond is half formed, right? right? So this would be the transition state, that high energy point where one bond's not quite broken all the way and one bond's not quite formed all the way. That would be the transition state. Notice these little double daggers. These are what we use to indicate a transition state. So if you see something, especially when it's in these block parentheses like this with the double dagger, that's meant to represent the transition state of a reaction. All right, and then let's take a look at a similar reaction, but one that occurs in 2 steps, right? I know that because there's one local minima here, and then I'm at my products too. This local minima is again going to be the intermediate of the reaction. So what does that look like? Well, it turns out that this reaction proceeds through a carbocation intermediate, meaning the first step is this bromine pops off. Then I'm left with this intermediate. In theory, I can isolate this carbocation. And then my chlorine forms a new bond with carbon. Right, but what's sitting at that minimum there is my intermediate, in this case, a carbocation. We're gonna see carbocations are the intermediate of like bajillions of reactions that we're gonna see in organic chemistry. All right, so the one last thing I'm gonna end with is with this idea of the Hammond postulate, which is something that will be more important later on, but it's worth saying now. Hammond's postulate was basically that the transition state, you can get an idea of what the transition state looks like by whichever end it's closer in energy to. Meaning for an endergonic reaction where the products are at a higher free energy than the reactants, they're closer in energy to that transition state, we'd expect the transition state to look more like the products than like the reactants. Likewise, in an exergonic reaction, and these actually should say, not thermic, but gonic. The transition state would look in an exergonic process or exergonic reaction with a negative delta G. You'd expect your transition state to look a little bit more like your reactants than the products. Again, this is something that, since we're not talking necessarily concretely about chemical reactions yet, won't be a big deal, but when we start talking about specific reactions and we're curious about what that transition state looks to, we're going to use Hammond's postulate to try to illustrate what that transition state is. All right, so make sure you know how to read and draw and interpret those reaction diagrams, those free energy diagrams, and then we'll move on to probably the 2 most important vocab words in all of organic chemistry, nucleophiles and electrophiles.